Okay, so if we go back to the previous slide, so the basic idea when we started doing the validation studies was we're trying to see if the validation results coming, how the validation of the simulation results would compare to the experiment. And there was a very famous paper on validation studies that more rigorous validation.
To really mute.
Yeah.
Tomas.
That is the.
Okay.
I'm going to start over. Are you recording this?
Yes, we are. Okay. That's fine. Let me start over.
You can cut.
Okay, so I can start from the beginning again. Okay, so the challenge was we wanted to be able to do more meaningful validation study for our transport models when we wanted to do comparison against experimental results. And the basic idea was moving beyond non-deterministic simulations to propagating the probability distribution throughout the computational model and then compare the results of that transport model with the experiment. So what we did here in this very first attempt as this UQ in the transport models is we try to come up with the heuristic model to propagate the uncertainties in the TGLF reduced transport model. So you can see here in the figures, we have on the right, we have input probability distribution of some of these uncertain parameters that we have into the transport model, and then we can use our UQ methodologies to calculate the transport, for instance, heat fluxes, the probability distribution of the heat fluxes compared to the experimental values which we're seeing in the left. Okay, so how the whole workflow would look like is something like what we see in the next slide. So basically, we have our transport module. So I believe for the previous OMFIT tutorials, we have seen how the trans module, how the TGLF module would work. Basically, what I want to add over here is how this is being modified to handle multi-sub-window uncertainties inside this TGLF module, so we would be able to propagate uncertainties throughout the TGLF module. So we have this trans module, and instead of extracting one plasma state from one sub-window, we're going to extract multiple sub-window values, and we need to convert those values into something that the GA code can read. That's why we're doing the profile gen, and after that, we're going to have the inputs of the TGLF scan, and we're going to have choosing some samples from that input probability distribution to propagate that uncertainties throughout the model. And I'm going to do a live demo of this TGLF scan module, and I'm going to explain how different things would look like as we do a UQ scan in the TGLF. Okay, so. Okay, so here we have the TGLF scan module loaded up in OMFIT, and we're going to take a look at one of the experimental cases to see how these uncertainties would propagate. So we can choose our state file, our G file, which has experimental values inside, and then we can go and load what shot number and what time in that shot number we want to do our analysis. So let me, for instance, I'm going to choose this ITER baseline scenario, shot number over here, and this scenario has two parts, two different phases of MBI plus ECH and MBI only case. So I'm going to focus for the uncertainty study of this MBI only case. I'm going to choose the time that corresponds to that value. Then I'm going to choose the transfer run that has been done so we can load the data over here. And I'm going to choose the time average window of 15 milliseconds. Other than that, the other extra feature that we're going to use. We're going to build all these input probability distribution of input into the TGLF based on the experiment. That's why we're loading multiple shots, multiple times, multiple sub-windows, so we can construct the input probability distribution based on that data. So I'm going to choose a couple of time slices, and maybe that's it. So for this case, I'm going to choose 5 sub-windows to get the data extracted. And how can we extract multi? Okay. Now, what OMFIT is doing is basically extracting the plasma states from the G file, and it's doing this over parallel multiple processors, so things are faster. Then we need to convert G file extracted plasma into something that the GA code can read. So we're going to run the profile gen. Again, the same profile gen is using multiple processors to get all these different sub-window values ready for the GA code. So after that, we need to set up the TGLF the way that we're doing a TGLF scan. Everything is familiar if you have done TGLF scans before. So I'm going to go, it's just doing things over multiple sub-windows so we can construct the input probability distributions. So I'm going to choose, for instance, I'm going to include the magnetic fluctuations, and I'm going to go set up the TGLF inputs over here.
Do you need to reorder the ions at all?
I'm going to choose only 2 ions for this case.
Okay.
So there is, in that sense, we can reorder the ions if you want to include more ions. But after setting up the TGLF inputs, I'm going to only choose the first 2 ions that I'm mostly interested in. But that can be done, again, like what Brian did with the TGLF scan, so we can reorder the ions based on need. So that's a very good time to ask questions, because this would take a minute or 2. We're extracting all these, we're setting up all these TGLF input values at all radii, and it's doing this over multiple processes, but it would take some time for TGyro to fetch all these inputs. So any questions?
How many radial points?
I think it's 100 radial points.
100 radial points. Okay.
What's it fetching exactly?
So right now it's producing the TGLF input values into the TGLF code. So right now, before that, we had the TGyro results, the TGyro power balance results, and we're producing A over LTI, A over LNE, all these inputs that TGLF requires at all radii for multiple sub-windows.
So technically, we could write something in OMFIT that would do this instead of going and running TGyro to get the inputs for TGLF. But then that introduces the possible error of having the code in multiple places. So
it's just a translator. It's a translator from a state file to TGLF just via TGyro, because the translation already is there and publicly supported by GA code.
Right.
Once again, not duplicating.
So after, I'm going to say what happens after this. So we have multiple sub-windows, multiple input profiles, input parameters for these sub-windows. So we're going to construct the input probability distribution based on these sub-window statistics. And after that, we're going to propagate that uncertainties through the computational model, come up with the heuristic model to approximate the relation between the response and input, which are the inputs of TGLF, and then we can compare the probability distribution of the response values, for instance, the heat fluxes against the experimental values. So the only difference here compared to the TGLF scan module is basically instead of doing 1D or 2D scan, we're going to apply the UQ over here. And okay, so I'm going to choose a radius to do the UQ scan over. So for instance, I'm going to do the row of 0.7. And I'm going to choose 2 ions and 1 electrons to be analyzed in the TGLF scan. So I'm going to have 2 ions, 2 main ions, and the electrons over here. So, but there are other parameters that can be played with, like what we have in the TGLF scan module. So we can go to the UQ scan, and what we can do here, we can determine what are our uncertain parameters. So for instance, we can choose how many uncertain parameters we want to have to propagate their uncertainties throughout the TGLF. So for instance, for the first study here, I'm going to do 1D scan of propagating ion temperature gradient A over LTI. And I can either define the probability distribution of this parameter myself, for instance, the type of the distribution, the parameters of the distribution, or I can say OMFIT to fit a normal distribution or a multivariate normal distribution to the experimental sub-window data. So if you want to do the comparison with the experiments, that's what we want to do. So I'm going to checkbox this one easily. So it's now for this 1 decade, it's reconstructing a normal distribution for A over LTI based on the multi-sub-window statistics. So then I can choose some samples and how many samples I want to take from that input probability distribution and how many parallel runs I want to have. So, and after that, I can easily run the TGLF UQ scan. And it's same as the TGLF scan, but now instead of doing the grid scan, we're sparsely, based on the sampling method that we have, choosing some samples from this input probability distribution and solving the simulation for those values.
Why did you have to change that to 16? Is it because it's at the nominal value plus 15 variations?
Yes, exactly.
16? Oh.
Yes, exactly. So what the OMFIT is doing is basically getting all these 15 samples plus the nominal value, experimental nominal value. That's why I added 1 more parallel processors to do that nominal value over here.
So I'm confused how it's subsampling. So I mean, it fetched some states previously for different radii, but at one time, right?
Yes.
So what's to sample?
At multiple times. So at different radii, we fetch multiple times based on the multi-sub-window values. So at one radius, we have multiple time values, and that corresponds to a probability distribution because there is an uncertainty in the sub-window statistics at one radius.
So where was that width of time?
In the beginning, when I was setting up the input profiles, I was adding all the sub-windows that I wanted. So there was a list that I added all the sub-windows. If we go back, we can add more sub-window values, shorter sub-windows, larger sub-windows, but we want to have something independent from each other. That's why we need to keep larger sub-windows, so all these different sub-windows would be uncorrelated from each other. That's how we can produce the statistics.
Okay.
And I'm going to show you when we were plotting against the experiment, how these samples and how the experimental value samples and probability distribution would look like. So what I can do after the runs are done, I can just simply plot all these input probability distribution and what we have as probability distribution of the fluxes. So I'm just going to click on this plotting routine. And what we're going to see here, this is the input probability distribution. So the black dots that you see over here are the experimental values for this A over LTI. And basically what OMFIT did, it fit a normal Gaussian distribution to these experimental values. And by choosing the sampling techniques, we chose 15 samples, which I'm showing here with the red dots, and plus the nominal value to solve TGLF for those values. And after solving for those values, we're going to come up with the heuristic model. Here, we're using chaos polynomials to model the relation between the response and input, so we can transform this input probability distribution throughout that heuristic relation and find out what is the probability distribution of the fluxes, for instance. So here in the second tab, we can, in the other tabs, we can see how the fluxes of the experiments versus simulation will look like. Let me maximize this so we can see what's going on over here. So for instance, for the particle flux, this is the relation between A over LTI and particle flux, and this is what the simulation samples would look like. So we can see how the chaos polynomial fit is being fitted over here, and how the response probability distribution, in this case, particle flux, probability of the particle flux from the TGLF would compare to what we have from the multi-sub-window statistics of experimental value coming from the power balance analysis. So here we can see there is some overlap between experimental value and TGLF, but TGLF is almost overestimating the experimental value.
So she explained why does the power balance, the black trans particle flux, why is that a non-normal distribution?
So what we're doing here, instead of showing the to enable showing the non-normality, we're fitting kernel density estimators. So it's another way of showing the histograms of the experimental values. And if we have more data, that would tend to be more accurate. But with the small number of samples that we have, we can see the samples are not normally distributed. That's why we are seeing in the kernel density estimators over there that this is not normally distributed. For other cases, we can also see even the simulation results can be non-normal, especially when we are near critical gradients, such, for instance, you can see for ion heat flux. So we have almost very small values, but it start to increase drastically as we go to higher values. But we have some sort of better agreement for the ion heat flux over here, but we are mainly underestimating the electron heat flux. We can also take a look at how the decision making for each of these chaos polynomials are being made in the console. So what I would like to show here is, let me, for instance, this is for the momentum flux, and from here we can see, if we look at the console, we can see how for different values of the chaos polynomial order, how this adjusted R squared is being calculated and what order of the chaos polynomial seem to be the best. So that's why how this decision making of coming up with the best heuristic model is being made over here. And we can also see that the OMFIT also calculates the statistical distance between these two probability distribution. That's something that can be used as a validation metric. So that was very simple 1D case. I just want to show that this can be easily extended. So now we're seeing, okay, A over LTI is an uncertain parameter, but I want to see, like, for instance, if I add A over LTE, how that uncertainty would change the results. So I can easily go and make this UQ scan dimension 2D. And now I have another parameter over here. Then I can choose, okay, what's the second parameter that I want to have in the scan? So I'm going to choose electron temperature length scale. And now what OMFIT is doing by clicking around TGLF scan, it fits the 2D bivariate normal distribution to the experimental data based on the sub-window statistics. And it's going to choose some samples and run those samples in for TGLF. So we're going to have another 16 samples, but now the samples are being taken in a way that covers a 2D distribution. Okay, so questions? That's a good time for a question.
Oh, I don't know why I did, but I mean, there's a point here that right now we're assuming the input distributions for like A over LTI, A over LTE are normal, but you're using this kernel density estimator.
Yes.
For the fluxes.
They're
both coming from that, those trans window subslices. So.
That's correct. One of the things that can be added later is basically, instead of supporting for multivariate normal distribution, supporting for the multivariate kernel density estimators. That's something that can be added to the TGLF.
Just treat them both as normal.
Yes, yes. Yes, that can, yeah, that's a better idea.
I had a question. Is there a definition of uncertainty for the when you have a non-normal distribution that you use normally, or?
So right now, the inputs into the TGLF in the TGLF UQ scan is assumed to be normal, but the heuristic chaos polynomial can support non-normal input distributions. This has been the first step, but we can support non-normal distributions or kernel density estimators or whatever distribution that is going to be inputted into the TGLF.
But the outputs are non-normal.
Yes.
So
Yes.
how do you estimate the uncertainty then? Do you have a standard uncertainty formula or standard deviation? Or
so all these probability distributions for response and input are normalized, and how this uncertainty is being propagated. So we're coming up with the relation between, for instance, heat flux and A over LTI. And this relation can be used to transform this input probability distribution throughout this relation and find out what is probability distribution of the heat flux, for instance. That's the formula. Basically,
yeah, I understand. Well, we can come back to that offline, I guess.
Yeah. Other questions?
Maybe what he's asking is, let's assume you have some experimental distribution, probability distribution, and you have a model probability distribution. How do you characterize how well those two match?
Oh, so the thing that we can, do is basically measure the statistical distance. So let's assume that this is not on the probabilistic level, right? Let's assume that we have one simulation for the experiment and one simulation for the one simulation and one experimental value. And the distance between these 2 points is how far the simulation is from the experiment. But let's assume that we have a probability distribution for the simulation results, and we have a probability distribution for the experimental observation. And measuring the statistical distance between these two probability distribution is what is it's exactly how far these two experiment and simulations are, and it's basically accounting for the weighted mean of that distribution. So you saw from this console that we're calculating the statistical distance using this Wesser time distance. That actually calculates what is the distance, the statistical distance between simulation and experiment. And that has the units of that flux value. So what that means is basically compared to the experimental mean value, how far this is, that can be a measure of how good the simulation is producing the experimental values. So you can see these two values are close because the expected value is around 0.40, but the distance between two probability distributions are much smaller than that. So there is a good overlap over here. So that can be used as a measure. Instead of measuring the distance between 2 points, measure the distance between two probability distributions. And that's what the code is calculating and showing in the console. So we can plot to see how this 2D TGLF scan would look like. Now we're seeing the input probability distribution being a bivariate normal distribution. And we have the experimental values. We have the best probability distribution that explains that experimental values. And we're choosing some samples from these 2D input parameter. And after doing the simulations, we can now compare and see how the experiment versus TGLF results would look like. For instance, here we see compared to the 1D scan, now the uncertainty in the TGLF is larger because mainly we are having two uncertain parameters here, but still we're seeing some overlap and some overestimation of probability distribution in the particle flux. We can do this. We can take a look at the same thing for instance, for electron heat flux, which I'm showing here on the left. And you can see there is a still underestimation of electron heat flux in this TGLF simulation, but now we have a better agreement for ion heat flux. So we can say, okay, we need to maybe tweak the A over LTE to see whether the uncertainties over there coming from maybe doing the T-gyro scan, whether we can match this with the experimental value or not, or doing more rigorous models such as gyrokinetic simulations instead of doing a reduced TGLF scan. So this whole uncertainty propagation scheme can be added to any computational model. This is a black box function that can be wrapped around any model. This can be also applied to gyrokinetics and has the capability. And I want to add this one to the end, that there are two ways to approach uncertainty quantification. If we don't have any data, it's better to come up with the heuristic model to propagate the uncertainties in any routine. If we have enough data, it's better to come up with the data-driven approaches such as Bayesian calibration or Gaussian process regression to propagate the uncertainties. So that's what we're doing here. What we're doing here is a model-driven uncertainty propagation method. Basically coming up with the heuristic model to propagate the uncertainties throughout the computational model when we have less amount of data. Any questions?
I mean, I think just kind of further elaborate, maybe, I mean, there's this Wasserstein, so there's an analog formula for basically, turning two different PDFs into some sort of scalar distance measure. And you could think basically, I think in the paper we were just about ready to submit, if you had two normal distributions, like there was the same width and some distance, then basically that measure just turns out it'll collapse to just the difference of the mean values in sort of a simple case. But if the two things are very distorted, non-normal, then it becomes something more like a weighted distance, depending on how much overlap.
How much skewness.
That's one formula for trying to come up with a scalar measure of quantifying the difference between the two distributions. You could do other things like just as calculate just the standard deviations or try to incorporate skewness or other things into some other measure. But yeah, I mean, there are in the statistics community these various formulas for
measuring the
some
distance.
scalar measure the distance between the two PDFs, and that's sort of what.
Yeah, this is the measure that we selected over here, but there are different statistical distance measurements that can be also implemented and added to TGLF as this module grows. Sure. Okay. So I'm going to turn this to Sergey for uncertainty package presentation.
I think as Chris mentioned, really the width that, you need to know the width and how separated the distributions are to really understand whether they agree or not. If they overlap but they're separated, then they could agree. And so anyway, that's, I guess, the characterization of the width is, I think, important.
Yes, that's already being included in this Wesser time distance that calculates that basically compares bin-to-bin comparison of one histogram to another histogram, one probable distribution to another distribution. So that width of the probable distribution is being considered in the Wesser time distance metric.
Okay, great. Thank you.
Mm-hmm.
All right, so to talk about, so this is kind of on one end of the spectrum where you have non-Gaussian inputs and non-Gaussian outputs also, where your model has some non-linear relationship, right, between the inputs and the outputs. If we look at the uncertainties package in Python, it takes the other extreme where it assumes that everything is linear in the uncertainty, both the inputs and the outputs. So I wanted to just show the documentation page for the uncertainties package for Python, and this is the main method that we use for tracking all sorts of uncertainties in in OMFIT, whether it be the uncertain data in like OMFIT profiles or MDS plus errors. They call them errors on the MDS plus side. We track those as uncertain values. So we can see here that the uncertainties package has something called a U-float. As you give U-float a nominal value and its uncertainty, then it will print out, if you ever print something, 1 plus or minus 0.1. So nominal value plus or minus the uncertainty. And it's good at propagating that uncertainty through various arithmetic operations. So if you do 2 times x, then that uncertainty becomes 2 plus or minus 0.2. And can also be propagated through various functions, if those functions have been instrumented to be able to propagate the uncertainty. So with that background, I wanted to show how we've used the uncertainties package to do one particular operation, which is the uncertainty propagation of a profile fit through a power balance calculation. So let me load a regression script here. I'm just going to start it running because it technically takes a while. So in this workflow, we're going to take the profile fits that have been done in Osborne's tools, and then we're going to take the correlated uncertainties from the profile fitting parameters and then propagate those the uncertainties in the parameters through the power balance calculation done by ONETWO. I have a small presentation here from APS last year. And so let me go to some relevant, okay. So fundamentally, what we want to do is we want to take inputs, run it through code, and get outputs. And more so, take some uncertainty in our inputs, use this wrap array func, which is inside of OMFIT, and get some uncertainty in our outputs. And that was on. Okay, so in the Osborne profiles fitting tools, a common profile fit is this tan-H fit, and it has these parameters. As it calculates the fit, it also calculates an uncertainty in each of these parameters, as well as a correlation of the uncertainties of these parameters. And this uncertainties package can take the calculated correlation between these parameters, and then we can construct uncertainty variables that have these appropriate correlations and propagate those correlated uncertainties through our calculations. So in particular, I show an example profile fit, which is the data in red and the fit in black. But then if you take the derivative of this, which is, as we know, the input to TGLF, as Payam was talking about, if you make sure and follow the correlations between the parameters, then you get the error bar in green. Whereas if you follow the, if you do not track those correlations between the parameters, then you get a larger error bar that's shown in blue for the derivative. And this is just taking a standard derivative, finite difference derivative on your profile. Great. So a little commentary on how propagations are uncertainties are propagated. The correlation matrix is this sigma f squared, and rather this sigma ij. That's the correlation matrix, and you can come up with the fundamental uncertainties, which are the eigenvalues of this matrix, and so then instead of having to track the full correlation matrix of n by n quantities, you can track only the relationship between a derived quantity and the eigenvalues. Anyway, so what we're going to end up with in our power balance calculations is we're going to run 1,2 multiple times. We're going to run it once at the nominal values of all of our inputs, and then we're going to run it once for each of the eigenvalues of the correlation matrix of our fitting parameters, and accumulate each of those results in the tree, and then from that we can take each of those results to be able to calculate the final uncertainty.